Okay, my name is Alec Pfundheller. I'm a graduate student in the Dr. G's Material Science 612 class in TEM, and this will be the video for my recording. For this project, I chose this paper. This is characterization of the microstructure of yttrium hydride under proton irradiation. Now, this was done by Stephen Toller, Fabian Nab, Takai Koyanagi, and Timothy Lack in a collaboration between Oak Ridge National Labs and the University of Michigan. Now, the reason I chose this paper is because Stephen Toller, I did an internship under him last summer at Oak Ridge National Labs, and this is one of his more recent papers, so I thought I could just shed some light on some of his recent work. Why are they trying to find the microstructure of yttrium hydride? We're trying to find better materials for moderating microreactors, since microreactors have to be a lot smaller than normal light water reactors or whatever. They need to use a very compact material. Now, for this compact material, usually we use metal hydrides because they allow the highest moderation per unit volume. Now, the current moderator that's being designed for microreactors and normal reactors is zirconium hydride. However, yttrium hydride is an attractive alternative because of its higher atomic density of hydrogen and better temperature stability under reactor temperature operations. However, very little studies have been done on yttrium hydride in relation to how it would behave in reactor conditions. So we use ion irradiation. This is the methodology they used for their experiments. They had 4 different samples of yttrium hydride. One used 1 MeV hydrogen ions, or 2 of them used 1 MeV hydrogen ions, 2 of them used 2 MeV hydrogen ions, and then 2 of them were irradiated at 300 degrees Celsius, and the other 2 were irradiated at 580 degrees Celsius. Now, these 2 temperatures were chosen because 300 C was the reference temperature to current nuclear fleet applications. So you can see this is sort of a lower bound of potential operating temperatures for yttrium hydride. Now, this upper temperature was chosen to be 580 because it's the upper range of a potential microreactor operation. However, it's below the estimated onset of thermal deabsorption from yttrium hydride, which is, I believe, about 600 C. So this is this is a pretty big upper bound for the yttrium hydride, so between 300 and 580 C. And then we irradiate all 4 samples to 0.2 dPa. Now, if you're unfamiliar with dPa, this stands for displacements per atom. You can think of this as a way to measure damage or measure ion damage inside a sample. So think you got like a 3x3 matrix of ions and you knock 1 atom out, then you would have 1/9 dPa. Then you have this graph over here. This is SRIM simulations of depth profiles of the different ion beams into the yttrium hydride. So we have this red curve. This corresponds to the 1 MeV hydrogen, and then this blue curve. This corresponds to the 2 MeV hydrogen beam. Now, they don't mention this in the study for some reason, but these dotted lines, this stands for the dPa. This is the damage the ions have created inside the material. Then this solid line, this is the injected interstitials or the injected hydrogen ions. Now, generally in ion beam applications, you want to choose an analysis area that's away from this injected interstitial area. Because if you're too close to this curve, you're going to get the injected interstitial effect where the injected hydrogen ions will combine with any potential vacancies and voids, and then it will mess up your data. And alternatively, you can't really do anything really too close to the surface because then you got the surface effect. You have a similar thing where the voids or dislocations would diffuse out to the surface and would also mess up your data. So generally, you want to do something sort of in the middle away from these. Now, the distances they chose for the 2 MeV hydrogen, they chose their analysis region as 10 microns deep into the sample, so around this area. And then for the 1 MeV hydrogen irradiation, they chose an area about 5 microns deep into the sample. So that would be around right here. So you notice there's an extra peak over here of a 2.8 MeV helium beam. So in part of their analysis, they used elastic recoil detection analysis, or ERDA, on their samples. So also part of this study, they're trying to find how well yttrium hydride retains this hydrogen inside reactor conditions. And they use IRDA, which is similar to RBS, to sort of detect how much hydrogen is inside, or detect the hydrogen as a function of depth into this depth into the surface of the sample. So you'll see that more later on in the presentation. So first off, they did some SEM and TEM images before they radiated the sample. So this is our SEM images of the underradiated yttrium hydride. Nothing really special here, just normal metal surface. And then B, this is a defocus or a very zoomed out image of the TEM lamella they got out the yttrium hydride and where all the different images are taking place. So you can see C, this is an under focused TEM image with no voids or nanocavities. But then once you move on to D and E, you can see regions of the sample where there are nanocavities. So you can see these small little white dots are probably hard to see from your perspective, but these are nanocavities. And then you can also on E on these little striations, you can also see some voids or nanocavities form along these. They said this is a result of the manufacturing process of the yttrium hydride. And then finally, we have a STEM annular dark field image, showing network dislocations. That look pretty cool. So after they irradiated, we have 4 different samples at 2 different irradiation energies and 2 different temperatures. And so you can, first off, you can see this little line here, 3 microns depth of the sample right here on all of these TEM images. This is the injected helium that was done before and after the irradiation. So all of these analyses are going to be taken way below this. This is to show the surface. Yeah, this is to show the surface of the sample of the hydrogen retention. Now, all of these look pretty normal. You can see large grain size, very high angle, except on the sample E, you can see this very strange, it almost looks like twinning. You can see just these little stripes form in the samples. And they didn't really know why that was, but it's very interesting to see this. And then they did some dislocation analysis. So this is the dislocation microstructure for each radiation condition. And now, oddly, you can see in specimen C and specimen D, they have a very high density of these smaller dislocation loops throughout the sample, or a high density of smaller dislocation loops. You can see all these dark little dots are the small dislocations. However, with the samples B and E, you can see they both see dislocations here, but they're reduced density and the larger dislocation loops. You can see there's a lot more of them in the specimen E. This is to be expected. It's at a higher temperature and at a higher irradiation energy. Now, before I go, these were imaged at different zone axes. So for most of these images are done in the 001 direction. However, for this image, it was done in the 011 direction. So after that, they did some void imaging as well. So voids were observed in all the samples. Now at the 300-degree samples, specimen B and C, voids are distributed very evenly throughout the sample. You can see these little white dots where the blue arrows are pointing to. These are the different voids created by the ion beam damage. But then as you go up to 580 degrees C, voids are only observed near the inclusions and the precipitates. You can see only these voids are included here near this inclusion and on here in this around this precipitate area. Now, this could have a very positive implications because at very high temperatures, likely the voids are diffusing out to sinks and they don't have a chance to swell. So the swelling rate at this higher temperature might be lower than the swelling rate at 300 C. And if that's true, then that'd be very good news for the yttrium hydride use in nuclear reactors. Unfortunately, on this paper, they didn't have time to do any detailed analysis of dislocation densities and sizes and void densities and sizes, so more work on this is needed. Now, finally, I mentioned the IRDA analysis earlier in my presentation. These are the results. So what are we looking at? So this is distance from the surface and all 4 of the samples, and then this is the hydrogen concentration near the surface. Now this E is all of the samples put together in a single graph. So samples B and C, i.e. all the samples are at 300 degrees Celsius, yielded very flat concentration profiles. You can see they're all around 0.61 degree, 0.61 concentration along the distance from the surface, showing no noticeable dip near the surface. And it's also lower than the pre-radiation measurements. So they're all lower on the pre-radiation measurements. But strangely, on samples D and E, they experience a lot more hydrogen loss near the surface. And in particular, this sample, it stays at 0.61 across most of the surface distance, but only in the first about 250 nanometers away from the surface, it drops down to about 0.57. But in the sample E, you can see it drops down to 0.54 and only goes up to 0.58. So there's a lot more hydrogen being diffused out of the sample on this more extreme condition over here, which was the 2 MeV hydrogen and 600C. So conclusions of their study, proton irradiation was conducted on samples of yttrium hydride to try to find a better nuclear moderator and microreactor capabilities. Now, hydrogen retention they found was primarily related to the formation of the dislocation loops in the voids, and the proton irradiation was successfully used to probe hydrogen transport and hydride moderator materials. More studies are needed on a lot of these, but I think the results look very promising. So thank you for listening, and yeah, thank you.